Hello everyone. So in this video, I will introduce the second part for this project. The project is, so this one. The project is the second project for distributed operating system. And the second part of this project is the multicast ordering. And actually it asked for two versions. So I implemented the FIFO ordering and causal ordering. If you want to know more about the first part, the clock synchronization, maybe you can refer to this GitHub report. But in this video, we will only focus on the second part, is this GitHub report, multicast programming and multicast ordering. So let's start with some background knowledge review. The three types communication forms in distributed system are broadcast, multicast, and unicast. Unicast is usually, sometimes we say, is peer-to-peer communication. And in the first project, the bank account management is the good example for the peer-to-peer communication. And also the first part of the second project, Volcanic algorithm for clock synchronization is also peer-to-peer communication. In the second part of this project, which is this GitHub report, we focus on multicast. And for multicast ordering is one of the most important issue in distributed operating system. There are three popular ordering algorithms. They are FIFO ordering, causal ordering, and total ordering. There are some difference between them, and if you don't know what they are, and if you don't feel familiar with them, I encourage you to go through this section and the below section carefully, and maybe you also want to review these slides, review those slides before you go forward. So let's go back to the second section, background knowledge review. So I assume I will run here, you know what they are, and you know what they are doing, you know how to do it, you know the theory behind that. In this implementation, I will implement the FIFO ordering and causal ordering. So generally speaking, it will multicast the message. This message includes the message you want to say, the sentence you want to say, the information you want to share, and also a sequence number. Someone calls it the clock value, your local clock value, or your local clock vector values. You multicast the message to all nodes in this distributed system. And also you will receive the message sent by other nodes in this distributed system. Each time you receive a message from other nodes, you will know their local clock or their local clock vector in their nodes. And then you need to, based on that information, to update your local clock. And these three ordering algorithms, they have different updating rules. And I encourage you to go through those updating rules step by step carefully, especially the FIFO multicast and the causal multicast, before you go further. And then we will introduce more details about this assignment. So even though this assignment only asks for the multicast ordering, but in order to make it easier for everyone to understand, I split it into two parts. The first part is multicast programming, and the second part is multicast ordering. In the multicast programming, I only implemented how to multicast the multicast socket programming, which is the base for the second part. In the second part, I implemented how to do the FIFO or casual ordering. So as I said here, before we go into multicast ordering, we need to implement multicast programming first using socket programming. And this is different from the basic socket programming, the basic peer-to-peer socket programming, like we did in the first project, bank account management, or the broccoli, sorry, where it is, the broccoli algorithm implementation. Those two, they are peer-to-peer socket programming. But for multicast, it's different. We need the multicast programming using socket. And below, in section 4, I list the details of those differences. So the second part for ordering, for the FIFO and casual, we need at least 3 processes, and each process will have 2 threads, one thread for sending message and another thread for receiving messages. We need to use clock or clock vector for clock synchronization, and we need to include this clock or clock vector in the message which we send. And of course, different ordering algorithm use different updating rules, as we just showed above. So, and then let's go into the details about the implementation. And also in order to make it easier to understand, I split it into 2 phases. The phase 2.0, I implemented the multicast programming. I use one sender and multiple receiver. The sender, I have a separate C++ file called sender.cpp, and the receivers, I have a separate C++ file called receiver.cpp. In the phase 2.1, I merged what I did in phase 2.0. I merged them into one files, into one process, and I implement what we are asked to do, that using 2 threads separately for sending and receiving. And in phase 3, based on what we did in phase 2.0 and phase 2.1, I finally implemented the FIFO ordering and the casual ordering. Actually, I didn't do the total ordering. So let's step into the first phase 2.0 and phase 2.1. They are a very basic multicast programming. I will explain why they are different from the peer-to-peer socket programming. So, so the multicast programming, I say, is different to the peer-to-peer socket programming. And for that, we also have a picture in this GitHub report that we need to do those steps in server side, and we need to do those steps in client side. We can say build sockets and set those socket options and band, and then listen and accept, then send or receive message. In the client side, we need build the socket. Also, we need the connect to the server socket, and then we need to send or receive message. But in multicast, it will be a little different. First of all, we of course we need build the socket, but after that, the socket operation, the socket option configuration is much more complicated than peer-to-peer socket programming. We need to configure the socket options and also the IP protocol options, including the IP multicast time to live and this if and multicast loop. In the client side or the receiver side, and we also need those IP protocol options configuration. There are IP add membership, which allow us to join to this multicast group, and also this IP drop membership, which allow us to leave the multicast group. And then the receiver need to bend. After that, they both can send to or receive from those multicasted messages. This part I show the color styles I will use in future sections. That the black color, it will show the definition of definition of functions or parameters. And this red color, I will show what we usually do in peer-to-peer socket programming. And in the green color, I will show what we usually do in multicast program. I put these two together on purpose to show the difference, so you can clearly see how different they are. And we also need to know the IP address range for multicast. When we do peer-to-peer programming, socket programming, you can almost set up all the IP address you want, especially when you are only build the local network. But for multicast, it's different. We have an IP address range to use. You can only use IP address inside this range. And actually, we also need to exclude this range. So the actually range we can use is like 224.0.1.0 to 239.255.255.255. If you want to know more about that, you can click into these links I refer to learn more about that. But these are the basic knowledge you must know if you want to do multicast socket programming. And so here comes to the first difference that when we build the sockets, in peer-to-peer socket programming, we use socket stream, which actually stands for TCP connections. But in multicast programming, we cannot use socket stream. We must use socket datagram, or you can also use socket row. But if you use socket row, it will be harder to configure it. So I will encourage you to use socket datagram. And I also list the difference between those three options. Usually the socket stream will give you a TCP connection, and the socket datagram will give you a UDP connection. And then after we build the socket, we need to set the socket options. We need to set up configurations. And actually, you have used this function in peer-to-peer socket programming, but usually we just set up to reuse IP address and reuse ports. That's the most popular settings we do for peer-to-peer programming. But for multicast programming, there are two parts we need to configure it. The first part is socket layer options. That's similar to what we did in peer-to-peer socket programming. The second part is protocol options. We don't have this in peer-to-peer socket programming, but in multicast programming, you must set up each. And about the protocol options, for receiver and sender, they will use different flags, or someone called options. I list all the options, all the flags we can use. So for the sender part or for the sending parts, you can use IP multicast if, IP multicast time to live, and more IP multicast loop. These three flags. So if you use the IP multicast if, it will set up the interface over which the multicast datagram outgoing, and the code will just look like this. We set socket options and we use this flag, and then use this option, and this address will be the interface of where we can outgoing over multicast message. Usually it will be a local address, and this address must be able to multicast. So before we do this, we must use this commands, this Linux commands, fconfig, to print out the local IP address we have, the interface we have, and in my local computer is actually this Ubuntu machine, virtual machine. It will have this address. It's 192, 168, 139, and 184. This one, it has the multicast app running, so we can use this one. And of course, we cannot use this localhost. So different machine, you definitely will have different IP address, and you must double check the multicast is running. If it didn't say that, then maybe you need to Google to solve this problem first before you go further. So for my machine, I just use this address with this multicast. The second option is time to live. The time to live to the range or message can go out. And I have listed the different numbers, what's their meanings. The default is 0, is 1. The default value is 1. The 1 means your multicast message will be sent to every node in this subnet. If you use 0, that means the message you multicast will be sent to all those nodes in the same host. And 32 means the message you multicast will be sent to all nodes in the same set, and so on. Because in this project, I only use one machine. I only want to multicast my message to multiple processes in this same machine. So I changed it to 0. And to code each, we just do like this. So in my case, my TTL is 0. And the third option we can use is IP multicast loop. The loop, if you set it to 1, that means you enable loopback That means you can receive the message use multicast. If you change it to 0, that means you cannot receive the message you multicast. In my situation, I want to receive the message I send out, so I want it to be 1, and the default is 1, so I don't need to change it in my code. These 3 options, they are for sending parts, and below 2 options, they are for receiving parts. You can use IP Edge membership, which will help you to allow you to join the multicast group. And to use it, you just set up like this. And this multi-address and interface, well, you just set it as what we mentioned about. The multi-address will be the multi-IP range, must be inside this range. And the interface is usually what we did here. Yeah. The second option you can use is IP drop membership. If you don't want to receive any multicast messages anymore, you just use this one. So below, I use those 3 canals to show how I configure my standard C++ file. As I mentioned in this phase 2.0, I have 2 separate files for sender and receiver. The sender is sender.cpp file, and the receiver is receiver.cpp file. So for sender parts, to set up the configuration in peer-to-peer programming, we only use this one to set up reuse IP address and reuse ports. But in multicast programming, multicast socket programming, we keep this. In addition, we also use the IP protocol options like I just explained. So firstly, I set the time to live to 0, and I call this function to set these configurations. And then I call this function to set the multicast if the interface. I didn't use the IP multicast loop because I want to receive the message I sent. So the default value is the value I want, so I didn't change it. For the receiver part, in the peer-to-peer socket programming, we don't need to change the configuration. But in multicast socket programming, we need to do it. First of all, we keep the reuse address, reuse port. On top of that, we need to bind, of course. And after bind, we need to change the configuration of IP protocol. I use add membership to allow me to join this multicast group. And after we finish the configurations, it's time to send and receive message. To send a message, we must use send to this function. We cannot use send function. We must use send to, because send function, it works only for connected sockets, which is peer-to-peer socket programming, TCP communication, what we did in project 1. But send to, it can work for both connected or unconnected sockets, like multicast socket programming, which is unconnected sockets. So we must use send to instead of send. And for receive, we can use read or receive from. We cannot use receive anymore because receive only used to connected sockets, the peer-to-peer socket programming. But read and receive from, they both can work for unconnected socket programming, the multicast socket program. So we use receive from, or you can use read. They are same. They are same. And here I provide a screenshot of how I run my code of phase 2.0. So I make first, of course, and then I run multiple receivers in separate multiple terminals. After I have 3 receivers, after I run these 3 receivers, I go to another terminal windows to run the standard. And then you can see the message. So sender start, it prints the PID, process ID of each. I didn't send some, oh yeah, I did. I did send a message to receivers. So receivers will read those message. So all those 3 receivers receive the same message because it's multicast. So the phase 2.0 is a very basic multicast example to show how to do it. And the phase 2.1 will be something more complicated on top of that. Because the requirement, it asks us to have 2 threads separately, 1 thread for sending message and 1 thread for receiving. So I have this phase 2.1 to do that. On top of phase 2.1, I changed it to using 2 threads. 1 is for sending and 1 is for receiving messages. So the difference is that in phase 2.0, they have their own process. Like we run it, we have sender and receiver. Sender and receiver, they are separate processes. And we have 3 processes for 3 receivers. We have 1 process for the 1 sender. But here, when we use 2 threads, the sending part and the receiving part will be inside 1 process. I use 1 thread for sending and 1 thread for receiving. So the structure will look like this. And when we run this one, they will just have 1 process. We don't have separate sending and receiving processes anymore. So the only difference is just I use 2 threads. So this screenshot shows how I run it. At first, I make it, of course, and then I just run the multicast try 1. So the try 1 and try 2, they are 2 versions. They both work. I just want to say how they are different. I just want to show which way I can use, which way is better for me to programming. So the try 1 version, it uses same socket file descriptor, but the try 2 version, I use different socket file descriptor for sender and receiver thread. Let me show you in the programming. So the try 1, I use same same socket thread. I use this main function. I build this socket, and pay attention to here. This variable is the socket file descriptor, and I set up the configurations, and then I call 2 threads. So pay attention here. I pass this variable to them, to sender and receiver. And then when we go to the sender, we are still using the same socket file descriptor. And we set the IP protocol options for sending parts and sending parts, the configurations, and then send message. For receiver, I pass this variable inside to receiver, so I'm still using the same socket. I band and then I set up the IP protocol options. You can see it this IP protocol configuration is different. This is IP add membership, but above in sender section, they are time to live and interface. And after set up the configuration, the IP protocol configuration for receiving section, and then we just receive message. So in the Taiwan version, I use same socket file descriptor. That's what I mean in Taiwan. And in Try 2 version, I use different sockets. So you can say in the main function, I don't have socket building function. I don't call the socket function to build the sockets. I just call those sender and receiver to parts. And in sender, I build the socket here. So the sender, it will use one socket and with its separate configuration and then send. For the receiver, it will has its separate sockets and its own configuration, and this is band and the configuration, and then receive messages. That's what I mean. I use different socket for sender and receiver. The Taiwan use same sender receiver. But these two ways for coding, they both work. So in this screenshot, I just show you how to run it. So first, I run what we have, and it will send the first 10 messages, because in the sender, I have a for loop to send to multicast 10 messages. This is a sender, and this is a for loop. This for loop to send 10 messages. And then after I receive those 10 messages, but at this time, at this phase, we have only one node in this system, that is itself. And then I open a second terminal. I run the second multicast process. So at this moment, we have two processes, that's two nodes in these distributed systems. And it will send the 10 messages, and it also receives that. So they both works. You can use one of them, or you can use mix if you want. The phase 3, we finally go into the ordering parts. So the phase 2.0 and the phase 2.1, they are basically multicast programming using two threads. And all further parts about ordering, we will based on the phase 2.1, which use two threads, and the Taiwan version, which use the same socket file descriptor for both sender and receiver. And in order to implement the ordering algorithm, I used some other helper functions to help me. I mean, before this, I mean, at this moment, we already did the multicast. We finished that, but beyond this point, we are focused on the ordering. That is the FIFO ordering algorithm and the causal ordering algorithm. You must be very familiar with the algorithm theory and the details if you want to go further. So I use some helper function to help me to control process, to count process, to help me to manage messages and so on. So this file, the process amount declare, is used to store how many processes you want or how many nodes you want in this distributed system. Because in the requirement, it say we can assume that the number of processes is fixed. That means we know how many processes will be there. So I use this file to store. When you run this process first time, it will ask you how many processes you want. You declare a number and you must follow the number you declared. If you say I want 3 processes, you must create 3 processes. And the second file is process counter. This one is used to really count how many processes is working in this distributed system. Only when these 2 numbers they equal, we will begin the ordering algorithm. So that's why I say if you declare a process amount, you must follow it. All below operations will be done on top of the condition that these 2 numbers equal. And then we finally talk about the vector clock data structure. So first of all, each node, they will have a local vector clocks to store their knowledge of the clocks of all nodes. That means in this example, if we have 3 processes, we have 3 nodes, the node 1, it will have this local variable. It's a vector, it has 3 elements. The first element is itself local clock, and this value is of course 2. The second element is its knowledge of node 2's clock. So pay attention here that this second element is just the node 1's knowledge of node 2's clock. It might be wrong. And the third element is node 1's knowledge of node 3's clock. It will be similar in the node 2. The node 2 will have a local vector variable like this. The first element is node 2's knowledge of node 1's clock, which might be wrong. The second element is the node 2's local clock, and this value is definitely correct because it knows itself. The third element is node 2's knowledge of node 3's clock, and it will be similar for the node 3. So this is a data structure. And this is a data structure for local clock vector. And then for different ordering algorithm, we will introduce later. The message they are sending, they will also have different data structure. I will explain later. So phase 3.0, I just implemented those parts I have mentioned, the process counter, process declared amount, the local vector, the local clock vector data structure. I implement all of them and all those proper functions. And they are able to multicast messages and receive messages. But we haven't using the updating rules of each ordering algorithm. So I call it no ordering phase, is 3.0.